Welcome to Quasar Does Astronomy. I'm your host, Quasar, and today we'll be discussing the conservation of momentum. So, let's say we have an isolated system of two particles, particle 1 and particle 2. Now let's say that these particles are on a collision course, and that they perform an elastic collision and then rebound. Now, conservation of momentum says that the total momentum before the collision is equal to the total momentum after the collision. Now, in order to look into this, we'll need to know what the equation for momentum is. So, the equation for momentum is defined to be momentum is equal to mass times velocity. Now, momentum is typically represented by P. So you'll see P equals M times V. However, that's just the beginning of this equation. So to look at the conservation momentum, we want to know that the final momentum is equivalent to the initial momentum. So typically we write that as delta P, or change in momentum. That delta looks like a triangle, and it means change over time. So delta P is equal to the final momentum minus the initial momentum equal to 0. This means that the final momentum is equal to the initial momentum. Now, we can rearrange that a little bit so that we can solve some problems and say P sub F for final momentum is equal to P sub I, initial momentum. Now, we can solve some problems with that, so let's go ahead and do that. Okay, so here we have an equation and a problem. So let's say we have a baseball that has mass of 0.145 kilograms. And I have a pool ball with mass of 0.17 kilograms. Now let's say that they roll at each other with an initial velocity of 1 meter per second. Now, if they collide elastically and roll away from one another, we have the pool ball with a final velocity of 0.5 meters per second. So, let's go ahead and calculate the final velocity of the baseball after its collision with the pool ball. So the first step we're going to want to do is we're going to want to write out what all of our variables are equal to. That way we don't get confused later on and use incorrect numbers. So we have M1 of our baseball, M2 of our pool ball. The initial velocities of both the pool ball and the baseball are the same at 1 meter per second to help make our math a little easier. And V2, our final velocity of our pool ball, is equal to 0.5 meters per second. So we'll go ahead and write out our equation. Final momentum is equal to initial momentum. And then we'll go ahead and plug and play with our variables. So when we plug in our variables, we get this line right here. And then we're going to combine those variables, and we'll combine those numbers and simplify it out a little bit. And we'll get 0.145 V1F plus 0.085 is equal to 0.315. So we'll go ahead and subtract 0.085 from both sides so that we can move it over to the other side of the equation. And then we'll divide both sides by 0.145. And that will give us V1F is equal to 0.23 divided by 0.145. And that gives us a final velocity of the baseball of approximately 1.6 meters per second. So now we know that the baseball would be rolling away from the pool ball at 1.6 meters per second. Okay, so now that we've figured that problem out, let's go ahead and look at another scenario. Now, I'm not going to solve this one out here. I'm going to leave that for you to do at home as practice. Go ahead and comment below what you think the answer is. So, for the problem, I have an astronaut with mass approximately 75 kilograms holding a wrench approximately 2 kilograms, and they're floating next to the International Space Station. So, from their frame of reference, they're both traveling at 0 meters per second. They're at rest. Now, let's say that astronaut throws the wrench at approximately 1 meter per second. Go ahead and calculate what the final velocity is of the astronaut in this equation and what direction he would be moving. Alright, that will wrap things up today for me in conservation of momentum. Tune in next week to see a video on the conservation of energy. we'll be looking at the conservation of energy and how we can solve problems with that, and how we can use that equation as well as the conservation momentum equation to solve even more complicated problems. I'm Quasar, and this has been Quasar Does Astronomy. Keep learning.